So in the last lecture, we have just introduced two quantities called as electron quasi-Fermi potential and hole quasi-Fermi potential. By using these components, we were able to express our current densities, electrons or holes, in terms of a simple gradient of these quasi-Fermi potentials. For example, if we have electron 1, so we will have just a simple expression. This component is corresponding to the conductivity of our electron gas, and this gradient of electron quasi-Fermi potential is working as a driving force of this current conduction. Of course, Jn assumed in this lecture is always a sum of drift component and diffusion component. However, by considering this electron quasi-Fermi potential, we can consider the synergetic effect of these two components. That was our main discussion in our previous lecture. Also, it had quite understandable boundary condition. If we have a boundary, then the value of electron quasi-Fermi potential and hole quasi-Fermi potential are just equal to the applied bias voltage. So now let's go to our case MOSFET. So now we have this kind of structure. Here we have y-axis as a channel direction. So it starts at y equal to 0 and ends at y equal to n. Here we have something called as a source region, and here we have something called as a drain region, and here we have also certain PR here. So this part, in the source part, of course we have a certain external circuitry which is eventually connected to the ground. So that is ground, and we have many layers of a metal line, but eventually that is connected to this ground, and here we have metal. So usually this metal sometimes can be certain good metal, and here we have a source which is typically made with highly doped N plus region or P plus region depending on the polarity. So its value, doping density, is, for example, 2 times 10 to the 20 per cubic centimeter, or even 5 times 10 to the 20 per cubic centimeter. Of course, when we make a comparison between these density, quite high density in silicon and the density of electrons in metal, even we have orders of magnitude difference between the number of electrons in silicon and metal. Means that metal has much more electrons even than the N plus or N plus plus silicon. But fortunately, since these two numbers are already can be considered as a quite high number, so that's the reason why this ground applied to supplied from this external ground can be safely connected through this one. Yes, that's true. And even between this source, external source and internal source part, we can neglect the voltage drop. So if you ask me, is it really 0? So is it really 0 nanovolt, 0 picovolt, 0 microvolt? I cannot say so. However, since the voltage difference across this system can be written as a VDD, because we apply 0 to the source contact and VDD to the drain contact, which can be orders of 1 volt, 0 point something. So small increase in this point can be safely regarded as quite close to 0. So in this case, although we have quite large area devoted to this source and drain, but in our electrical sense, actually this can be regarded as the starting point of our most important electrical part. And also here you can see that this is the end of our channel inside of our drain, and also here we have a drain contact. We have applied VDD, so VDD voltage can be applied up to this interface, metal and silicon interface, but still we have quite small, relatively small resistance compared with quite high resistance in the channel, so we can neglect the voltage drop occurring in this highly doped drain region. So that's the reason why now we safely say that okay, this point is also biased with VDD. So now if we consider this system, although we have a certain surrounding source and drain, but they are treated as a secondary effect, and we just think that the only important part in this MOSFET is the area underneath our gate contact. Where can you find the gate? Yes, here we have a gate, and underneath that gate we can find the silicon dioxide layer, which is extremely thin. Below that layer we can find a plane which is surrounded by or covered by gate contact, and this part becomes quite important and electrically only meaningful part of our system. So now you understand the voltage, applied voltage to this point can be regarded as 0, and this point can be regarded as VD, drain voltage. Then natural question is, then what will be the electron quasi-Fermi potential at this point, and what will be the electron quasi-Fermi potential at this point? The answer is quite straightforward. The answer should be yes, there should be VD, and there should be Vs source voltage, but happen to be, we assume that source is grounded, so we can say this one becomes 0. That is the situation we wanted to have or we wanted to assume in this analysis. So that is the starting point. We have to say that at least for quasi-Fermi potential, electron quasi-Fermi potential, we know two boundary values. Now let's think about the solution of this system at equilibrium. So now think about this one. We have a certain value of a gate voltage, for example 0, 0.3, 0.5, whatever. We can expect any value for certain gate voltage, and now let's say that VD equal to 0 volt. So in this case, please try to estimate your solution for this system. Now you have y-axis, and your system starts from y equal to 0 and ends at y equal to L, the channel length of your system. And after that, now you have a certain depth scale, so that is x, and it starts from 0, that is corresponding to the interface between your silicon and silicon dioxide. Then where can you find your oxide or metal gate? Your metal gate can be found somewhere here, and its x position would be minus T ox, which is quite short, and beyond that point here you can find a gate terminal. Of course, in our notation, x value which is lower than minus T ox, this part is assigned to our gate terminal. However, we do not care about this gate terminal at all. Only the role of this gate terminal is just to apply certain boundary condition for our Poisson equation, and that point will be given here. So now, if that is the case, certain gate voltage is applied. Yes, we understand. And also certain drain voltage exactly 0 is applied. Then what will happen to this guy? Now, in this case, what we can say is phi n equal to what? Just 0 volt. And please try to answer my question. What will be the value of phi n? So its value will be also 0 volt. Two boundary values are set to be 0. Then my question is, do we have any chance to have variation of this quasi-Fermi potential? For example, let me just say your phi n just looks like this. If that is the case, then what will happen? If that is the case, then we will have certain current conduction, because current is obtained by taking the gradient of our quasi-Fermi potential. For example, here we have a non-vanishing gradient of our quasi-Fermi potential. Also here we have a non-vanishing gradient of a quasi-Fermi potential. It strongly means that at least in this point, our current density should follow minus q mu n, and also d phi n over dx, gradient of this quasi-Fermi potential. So simply means that if we allow any kind of non-vanishing gradient of electron quasi-Fermi potential, the answer would be we should allow non-vanishing current density at a certain point of our device. But you know that now we apply 0 volt and 0 volt to our two terminals, source terminal and drain terminal. And if we say, although we apply 0 volt, we have current conduction, that makes certainly some contradiction to our understanding on this physical behavior. If you apply 0 volt to your drain terminal, you should have 0 current. That is quite obvious. So simply means that we cannot allow this kind of any variation in our electron quasi-Fermi potential. The answer is quite clear. The answer should be all over I over our y-axis, our quasi-Fermi potential at this specific 0 drain volt. So regardless the value of your y position, it should vanish. So 0 all over our case. So simply speaking, since this one is just a constant, now we will have 0, so there is no current at all. Yes, we are quite happy with this kind of explanation. So since we have applied 0 volt and 0 volt, and inside the system, inside the channel, we have 0 electron quasi-Fermi potential. So by taking its gradient, we will have just a vanishing gradient. So we don't have any kind of current conduction. Then, if that is the case, now it means that if we pick up any point, any y point, our answer is phi n equal to 0. It means that every point is the same in terms of its applied gate terminal. All of them share the same gate voltage, and all of them share the same electron quasi-Fermi potential. It means that all of them, any point in this system, are identical. We have just one-dimensional problem. Although we have y-directional variation in principle, but by applying just 0 volt to our system, or the voltage equal to source to our drain, then this channel becomes just homogeneous along y variation. So now the solution of this system becomes quite clear. Just a solution of our MOS capacitor by applying certain gate voltage. So you know that we have to divide our VG minus V flat band voltage into oxide potential and surface bending. So by solving this equation, we can calculate this surface potential, and also from this one we can calculate a semiconductor charge. That was our discussion in the MOS capacitor. Same argument can be applied to this system exactly without any modification. That is the starting point of our discussion. Now we have device. Now we have a Y dimension. But when we apply 0 volt, everything is just completely normal and nothing new. Only complication occurs when we apply now non-zero value of this drain voltage. Now, we certainly know that electron quadriform potential vanishes at this point, and it does not vanish at this point. If I draw, for example, Y and draw phi n, certainly it hits this origin, because here we have 0 and L. Yes, this one is given by our boundary condition. But when we have non-zero boundary condition or non-zero bias voltage for our drain, then it means that now we have a certain non-zero value for VD, which is equal to phi n at position equal to L. In this case, the question is, what is the intermediate behavior of our electron quadriform potential? That's the main problem of this situation. So, for example, maybe you can say, why don't you just assume straightforward line? Yes, that can be one solution. Or why don't you just consider parabolic behavior, this upward one? Or why don't you just consider other one like this downward one? So what will be the proper solution of this electron quadriform potential? Depending on this electron quadriform potential, it will predict different behavior, and among many different possibilities, there exists only one single solution, because when you apply certain gate voltage and wait for a long time, then you will have the steady state solution, and there exists only one solution which is suitable for this situation. So we will try to find out the form of electron quadriform potential, and also surface potential and electron density from this non-zero drain bias voltage case. Okay, so this is just a description about our problem. Why do we have such a complicated problem? Because we now introduce this new dimension called as a channel direction. Y-axis is allowed it, and also we allow spatial variation along this y direction. So we must solve something which depends on y position, and that is the main point. So it is clear that in this problem, the main quantity of our interest is electron quadriform potential. We wanted to calculate it as a function of y, so different position. Then maybe you can ask me this question. Okay, now I understand. It is very important to know what is the value of this position and what is the value of electron quadriform potential at a different position. Now we will try to solve this one. But before starting the discussion, I have, or you may have, quite an obvious question, and please have a look at this point. Our domain is no longer one-dimensional. Our domain is now two-dimensional. We have to consider x and y simultaneously. You can ask me this question. We have even z direction. Yes, but why we do not consider this a z direction? In our planar MOSFET technology, this z direction is just working as width of our transistor. But by adding wider channel, we just say that wider channel just to have more conductivity due to the more width. So this g directional width is treated as just a secondary impact. So this is not that important. We just multiply with W to our current density to eventually get drain current. So we treat that among three different axes. So this one is really trivial. We will just assume homogeneous or uniform distribution of our physical quantities along g-axis. So that's the reason why this one is not that important. But other ones, x and y, they are really important. What is x? X is vertical one, and the direction for confining electrons or getting more or less electrons. This one is the most important one. And now we have the next important one, y, which allows current conduction. So let me just come back to our question once again. I told you that we have to calculate the electron quasi-Fermi potential at a certain y position. Then question is, how about this one? Electron quasi-Fermi potential in general can be regarded as the x and y dependent quantity. Do we have any can I say guarantee that values of electron quasi-Fermi potential at this point is equal to the one at this point or that point or other point? So can you say that this point, oh sorry, so I drawing it a little bit tilted. So can we say that the value of electron quasi-Fermi potential is equal to that one and that one and that one? Is there any guarantee that we have all shared value of electron quasi-Fermi potential along x-axis? I'm asking this question because almost immediately I have written in this way: phi n at only function of y. So I just omitted the dependency on x. Why we can do this job? That is another question we have to answer correctly. Okay, do you have any idea why we don't have this x directional, vertical directional variation? So let me just do it. So say that now we have a certain phi n x comma y, and now let's say that also now we have x plus delta comma y. They share the same y position, and let's allow a little bit different vertical position. And now let's say that they are not identical. We can allow a little difference. So it means that we now allow the gradient of electron quasi-Fermi potential with respect to the x-axis. Then I wanted to ask you this question: what is the consequence of this non-zero, non-vanishing gradient along x-axis? So now Jn, that is a vector quantity, and it should be regarded as certain conductivity and gradient of quasi-Fermi potential. Everybody know that this gradient is once again a vector quantity, and we have to have this one, q mu n n. Now we have x directional unit vector and partial derivative with respect to x direction. And now we have y directional unit vector and partial derivative with respect to y-axis. I'm just writing down the definition of gradient operator. And if I go further, then we have to have, of course, g-directional unit vector, which is multiplied by g-directional partial derivative. That is the general form for our gradient of electron quasi-Fermi potential. But in our notation or in our system, we can safely say that this g-directional partial derivative does not exist because we assume that everything is just uniform along g-direction. So this is just trivial. But point is, if we allow this general form, then now we can say in this way. Please try to calculate x-directional component of your Jn. And please try to write down y-directional component of your Jn. Simply speaking, if we write down x-directional component of this vector field Jn, then we have to write down minus q mu n, that is shared, and finally we have to have phi n partial derivative with respect to y. And if we have to consider y-directional component of Jn, now we have to have also same leading coefficient, but only partial derivative should be taken with respect to y. So that is the point. Simply speaking, if we understand this kind of a discussion, now we know that so sorry about that. This is not the case. Simply speaking, this one x-directional vertical directional current conduction is generated by the x-directional variation of electron quasi-Fermi potential. So if our electron quasi-Fermi potential varies along vertical direction, then we have to, at the same time, we have to allow non-vanishing current conduction along this vertical direction. Please think about this one. In our case, now we have source and drain. And here we have applied voltage difference between source and drain. Then what will be the direction of current conduction? Of course, in this case, since the voltage difference occurs along y direction, now we expect that there will be current conduction only along y direction. We can expect that is not zero, but we do not expect this kind of current conduction. Although we have applied voltage difference in this y direction, but can you expect current is flowing this vertical direction? So, and do not arrive at drain eventually. Can you? So this one is not corresponding to our physical intuition. So current should follow only y direction, and vertical direction current conduction should be almost negligible. So simply means that from our intuition, it should be almost vanishing. Then how can we neglect this kind of J and X component? Our answer is yes. Now we have to admit that phi n, electron quasi-Fermi potential, does not vary quite rapidly along this vertical direction. If we allow that case, then we have to have vertical current conduction, and for this system, it is not allowed. Okay, so now we can say that that's the reason why, although phi n itself can be regarded as a function of both of a function of x directional position, vertical position, and y directional position. But when y position is given, then our quadriform potential is shared by all vertical directions. So that's the reason why now instead of this one, now we introduce a new notation V. But this is nothing new, and just showing that channel region share vertical channel region at a given y position just to share electron quadriform potential. I'm just write down in this way. Do you have any question? I think that this is one important thing we have to understand for understanding this argument or model development. So simply means that if this one phi n equal to 0.3 volt, and nearby this interface, all of these points will have phi n equal to 0.3 volt. Therefore, we will not have any kind of x directional current conduction. Before moving to the next slide, I have the final question to you about the validity of this assumption. So now let's say that this one is corresponding to x equal to infinity, really deep substrate. Now we have just p-type substrate. Then if I ask you once again, what is the value of your phi n? Now let's say that your body or substrate is grounded. Then what will be the value of your electron quadriform potential at the deep substrate? So can you still say it should be 0.3 volt because they share the same y position? The answer is quite clear. In this deep substrate, its quadriform potential, electron quadriform potential should be 0.0 volt because it is grounded to the body, and it is connected to the body, and body is grounded. So seems to be there is some contradiction between my two arguments. Since this point is attached to the body, we have to have its body voltage, and which is assumed to be 0. And since they share, this part share the electron quadriform potential, they all have a certain value, non-zero value of electron quadriform potential. Then what's the problem? If we extend this discussion till the end, till the deep substrate, then we have to say that phi n should be 0.3 volt. Certainly it's not the case. Then where do we have a contradiction? This kind of discussion is related with our assumption that Jn should vanish. Yes, Jn should vanish, but there is actually two different ways to make our Jn almost negligible. Please name them. I just told you that one way is to make this d phi n over dx almost equal to 0. That was the physical origin of this homogeneity of electron quadriform potential. But you have another different way to make it 0. What is it? If you have almost vanishing electron conductivity, then regardless the value of your gradient, you will have also 0 current conduction. Simply means that if you don't have any electron at this point, then it doesn't matter you have a certain value of electron quadriform potential. Simply speaking, for almost no electron zone, you are allowed to have any variation of your electron quadriform potential. That is the point. Now, in this MOS case, when you apply your device in its weak inversion or strong inversion region, now you have a relatively high density of electron gas. And now in this deep substrate, you have almost vanishing electron density. So your system, MOS system, can be divided into two parts. One is highly populated electron part, and you have lowly populated electrons. Then in this case, for this highly populated one, you should have constantness of electron quasi-forming potential. But beyond that point, then you have freedom to have varying electron quasi-forming potential. So simply speaking, in this case, where can you find a drop of this electron quasi-forming potential? Yes, somewhere between this deep substrate and channel region, you have a change of electron quasi-forming potential. So there is no contradiction in this discussion. Please note that this phi n, the constantness of phi n, should be regarded as only within your channel region. So nearby the interface, you can assume. Nearby means that just nanometer scale distance from this interface, you can assume the constantness of your electron quasi-forming potential. So now let's go to this one. Now, so when we say v, which is a function of y, it means that for x, which is quite close to 0, every electron quasi-forming potential is equal. Okay, so that is my assumption in this model development. Okay, so we just finished the problem specification for our system. Now we have quite a well developed model for this case. Although in general we must consider phi n all over our 2D space, but fortunately by using the vanishing j and x component, so we made a great simplification. Now our variable just becomes v of x, electron quasi-forming potential, which varies only along y direction. So by knowing this quantity, then we can solve this problem. That is a great simplification. Okay, so now today's main topic is so-called gradual channel approximation. Gradual channel approximation should be considered. Up to now, we have talked about this phi sub n, electron quasi-forming potential. And you know that this electron quasi-forming potential is related with electron transport. So by knowing this phi n, now we can calculate Jn. So this is all related with how our electrons are moving. But please remember that in order to analyze this system, we need two different approaches or two different considerations. One is Poisson equation. So how many electrons are gathered by electrostatics, and another one is electrons movement or electrons transport. So we have to understand this one. And now our question is, now previously in our MOS case, we just solve 1D problem, x directional problem. But now our domain expanded to the 2D problem, so we must solve in general xy problem. Our Poisson equation in 2D plane now should be written in this way. What is the difference? Previously we had just a second derivative only respect to the x position. Vertical directional component was important, but now due to the expansion of our simulation domain or calculation domain, now we have to consider this y directional second derivative. that should be considered in general for our Poisson equation. So this is the general case. But gradual channel approximation simply states that, this is quite important, this is generally valid one, but in this gradual channel approximation, we simply neglect this second term and say that Poisson equation becomes just once again one-dimensional Poisson equation. That is key assumptions or key approximations we are now introducing to this calculation. Actually, solving this partial derivative with two independent variables are much more difficult than just 1D problem. So that makes a greater simplification for our model development. Then, of course, we have made an approximation, so we have to justify ourselves why we are allowed to do this job. How can we justify ourselves to neglect this term? That is quite simple. Here and there we have two terms, and we just say that since this first term is so important, so the magnitude of this second term can be quite small or negligible. So although that is not exactly equal, but with good accuracy, high accuracy, we can introduce similarity to this point. That is our assumption, but maybe you feel that, is it really allowed to do that? Yes. Think about this one. What is meaning of these two terms? Let me just think about this one. This is a small box, and this is y position, and this is x position. The first term, the second derivative of this vertical direction, simply means that there will be certain electric field, and also there will be certain electric field, because this guy is related with the x directional derivative of our electrostatic potential. Also this one is related with x directional derivative of our electrostatic potential. Their difference, the difference between this and that, is corresponding to the second derivative of our electrostatic potential. So simply speaking, this one is once again the partial derivative of x directional electric field with respect to the x position. Of course, it's a negative sign, but this is corresponding to our first term. And now we say that the variation of a vertical electric field is quite rapid. Why do we say so? Because now we have a strong electric field sent from our silicon dioxide layer. Now we have a strong surface electric field, and inside this system we have a lot of electrons, and by these electrons, inversion electrons, now this high electric field is already quite rapidly, in the spatial case, rapidly compensated, and now we have a relatively weaker electric field along this g direction or vertical directional one. Because this system is driven by the difference between gate voltage minus flat band voltage. This is the overall our voltage margin to drive this vertical MOS system. And please note that flat band voltage is about -1 volt, and our gate voltage varies from 0 to something. So it means that along this vertical direction, we just apply certain 1 point something volt across our MOS capacitor, and almost all of that potential difference is divided by what? Divided by our oxide layer. Yes, it takes some. And remaining part, surface potential, that is highly concentrated only nearby silicon silicon dioxide interface. It means that now in this MOS system, we have a gate and substrate. Their overall voltage difference is about VG minus flat band voltage. Yes, this is quite a high value, like 1 volt or even higher. And oxide has something, Vox, that can be certain value, 0 point some volt can be consumed by this oxide layer. Yes, it is not negligible, but remaining part. So this one is corresponding to phi s. You know that this is quite high. This is, for example, even close to 2 times phi b, so 2 times of bending to have inversion condition. So this is about 0.4 or 0.5 volt. Still, its value is almost 1 volt. This 1 volt difference occurs widely spread over this entire semiconductor region. No, this voltage difference is highly concentrated only nearby this channel region. And you know the thickness of this channel region. It is just orders of or thick channel and depletion region, and its length scale is just 10 nanometer or slightly wider. So 1 volt is just applied within a few 10 nanometer scale. That is the situation. Now, let's think about our long channel approximation. How long is it? It is orders of micrometer scale. And how large is your applied voltage? Your applied voltage at most a few volts. You may apply 2.5 volt, 1 volt, 0.7 volt. And this is distributed within just micrometer scale. So even at this, the worst case, you can certainly say that due to the long channel approximation, y-directional electric field cannot be comparable to this vertical structure. Simply speaking, in our case, our system in this case, we may expect that about 1 volt is applied, and within just orders of 10 nanometer. That is a vertical situation. And at the end of this journey, if we arrive at deep substrate, electric field should vanish. Here we have almost zero electric field, and here we have quite a strong electric field, and that varies within just a short distance. That is the situation. So now we can say that if we have a surface electric field and the field at deep substrate, this one is a deep substrate, almost we have no vanishing, and the distance is about the width of our depletion layer. That will be an average variation of our electric field across x directional one. But please think about y directional one. Then what is this maximum average electric field along y direction? Y direction, we have a channel length L, and voltage difference is VDD. Then it is now clear that this one is actually y directional electric field itself, but you know that since this is just values of a y-directional electric field, if we take its variation, we can also expect that since its value itself is not that high, if we take its gradient, so it would be also negligible to that of our x-directional variation. So I'm spending quite a long time, almost 10 minutes to justify this gradual channel approximation, but it is known that this is really true for almost all operational regime. So you can safely accept this gradual channel approximation, but there is one exception for validity of this gradual channel approximation. If we go to so-called saturation mode of our transistor operation, then this is not the, maybe this is not the case. Now this second part become comparable to that of our first term, vertical variation of electric field. But in that case, maybe you remember that when you study your MOS IV characteristics in the microelectronics course, what happened? You just consider just triode model region, and beyond that triode model region, you just say that something called as a saturation occurs and current becomes just constant. That was your study. So in usual textbook, we do not care about the exact modeling about saturation mode. So for Y, although this gradual channel approximation cannot be applied to the saturation mode, but except for that, this can be applied to every other operational mode. So please accept this consideration. So maybe some of you guys are not very happy with this approximation. Oh, I wanted to proceed without any approximation. But you know that if you really wanted to do that, then please write down your computer program to numerically solve this problem. We are doing this job to make analytic expression. If we are allowed to spend a large amount of computational power, then actually we don't have to spend one semester for this problem. We can just learn program, and after waiting for several minutes, then we will get the solution. But our purpose is to develop a certain simplified model with reasonable assumptions and improve our understanding on this problem. Okay, so I think that now we have covered two important components of our discussion. One was, although the appearing order or presentation order was swapped, one was about Poisson equation. In order to solve Poisson equation, actually we have to solve 2D Poisson equation, but we made a bold assumption that, oh, no, we are allowed to just solve one-dimensional Poisson equation. So that is great simplification, and this is called as a gradual channel approximation. And another one is about electron transport. Although electron transport, in order to consider electron transport, we have to consider electron quasi-Fermi potential, which is a function of both x and y coordinate, but also we made quite a bold approximation, like, okay, along vertical direction, the electron quasi-Fermi potential is shared. So now we are allowed just to y-directional quantity, v of y. Okay, these are just to generate much simplification. Poisson equation now becomes just x-directional one. And now electron transport, electron movement now becomes just y-directional one. Electrons are moving only y-direction, and our electron density calculation can be done only vertical direction. So we are now a set of two one-dimensional problems, although they are not sharing the same axis, but x-axis is used for gathering electrons and y-axis is used just pushing them to allow current conduction. That is our great simplification. Okay, so at this point you have to, in my opinion, you have to feel the beauty of this course. If you cannot feel the beauty of this course, then maybe so because you know, I think that this is the most beautiful part of our entire semester. Later on we will see a lot of approximations and everything becomes getting dirtier and dirtier, but I think that this is really beautiful to have these good approximations. Okay, so now then you can ask me this question. Electron density. In order to calculate electron density, we must solve a Poisson equation. Then in Poisson equation, we have an expression for electron density. Here we have the expression for electron density. Then how can we express our electron density? Previously, our model for electron density at any position was written as this form, Na exponential phi over kBt over q. So please note that when we say in this form, this phi should be considered as the one referenced to our deep substrate. It means that it is referenced to the positive infinity position. So maybe you remember that sometimes I introduce unofficial notation like tilde phi to make a distinction between our usual convention and the reference to the deep substrate. So anyway, we are currently using the value referenced to the deep substrate, and that was our previous expression. Then question is, now we introduce different assumptions for electron quasi-Fermi potential. Please let me explain a little bit further. So now let me draw MOS capacitor. This one is a gate, and now we have a silicon dioxide, and now we have a silicon. And previously, when we consider this MOS capacitor, our important assumption was this part. Now we have a phi n equal to 0 volt. That was our assumption. Do you remember our assumption? And the justification of this 0 vanishing electron quasi-Fermi potential was provided by the existence of this substrate contact. Substrate contact was connected to the ground, so it dictates that every point phi n and phi p equal to 0 volt, and along this direction, so this is just spread, so we must have 0 volt. But now in our new consideration within the gradual channel approximation, our configuration becomes a little bit different. So please allow me explain a little bit more about this one. Now it is in our new configuration, it is still true that phi n and phi p should be 0 at this deep substrate we have already discussed. And in the case of our electron quasi-Fermi potential, now we have phi n equal to V. So the one shared by all our channel electrons. Of course, in between, what happens? There will be the transition from V values to the 0 values within certain position, and we will have just zero values. So we don't care about this point or that point because there are not many electrons at all, and electrons are only found at nearby this surface, so we will use this phi n value for our electron calculation. Next question is, how about hole quasi-Fermi potential? Hole quasi-Fermi potential. Here we have a lot of holes actually in deep substrate, so it is certain that our hole quasi-Fermi potential is just kept as 0 up to certain point. And the next question is, beyond that point, what will be the value of our hole quasi-Fermi potential? My question is, can we assume that hole quasi-Fermi potential is equal to that of electron quasi-Fermi potential? That is my question. And the answer is obviously no. When you draw your hole quasi-Fermi potential for this MOS system, this is nothing related to your, how can I say, your source and drain region. We have the tendency to see this MOS system from the viewpoint of electrons in many cases. But please try to visualize this MOS system from the viewpoint of your holes. Then how does it look like? Your viewpoint of holes, so you have a certain part which is dominated by your holes. You have so many holes. Yes. Then, of course, nearby your surface here, you don't have many holes. Yes, your hole density is quite small. Holes are depleted. Yes, you are right. Then, question is, how many holes are found here, source and drain? So please try draw your own letter for P. Here I used quite a large P to show you high hole density. Now I introduce relatively small p to say that there are not many holes. Then if you are allowed to write down something, draw something at this source and drain position, how many holes are there? Of course, a small number of holes, low density, but please make a comparison between your channel hole density and source drain hole density. It is certain that even compared with your depleted channel region, your hole density here is even lower. For example, if your doping density is 10 to the 20 per cubic centimeter, then what will be your hole density? Your hole density will be just 1 per cubic centimeter for your source, and of course for your drain. Then how many holes are there? There are holes orders of 10 to the something, 10 to the 3, 10 to the 4, so almost no holes. But even when we make a comparison between this and that, now we can say that source and drains are least populated by our hole gases. So simply speaking, in this case, now we have source voltage, now we have drain voltage, and they try to specify hole quasi-Fermi potential. But you know that variation of this quasi-Fermi potential only occurs the least populated part, because more populated part do not allow any kind of variation. If we allow severe variation of quasi-Fermi potential, then there will be strong current conduction. Simply means that when you make a comparison between this source drain part and all other part, they are highly populated by holes and they are almost empty, not populated by holes. So drop, variation of your hole quasi-forming potential only occurs within this source drain region. It means that what will be the value of your hole quasi-forming potential at this point? This point, you can certainly say that it will be just 0. Why it is 0? Because substrate is grounded. That is my consequence here. So, simply speaking, we have to consider both electron quasi-forming potential and hole quasi-forming potential in this MOS capacitor. But my discussion about increased quasi-forming potential somewhere along the channel, introduction of Vy, all related only to our electrons, because here we have a lot of electrons. But in our whole case, source and drain is not working as a carrier reservoir. That they do not play any role. So in the case of our whole gas, the only important contact is substrate contact, and substrate contact just to say that it is grounded, so it should be regarded as 0 hole quasi-Fermi potential. So simply speaking, now let's come back to our previous lecture course. Now we had this kind of behavior. And also, for example, if we consider whole gas, then it should be regarded as this one, minus phi over kBT. If we have non-zero electron or hole quasi-Fermi potential, what we have to do is just to modify, consider this one, electron quasi-Fermi potential and hole quasi-Fermi potential. That is required. However, in our whole case, phi p, hole quasi-Fermi potential, can be still safely regarded as just 0. So our previous assumption for hole density can be used any modification. So it is completely okay to reuse our previous one, but only for our electron gas. Now electron may have different electron quasi-Fermi potential, so we have to now introduce this V of Y to modify the expression for our electron density. So now you are looking at the expression, new expression for your electron density. Simply speaking, if we have a certain Y position, then now you have a non-zero electron quasi-Fermi potential. By using this non-zero electron quasi-Fermi potential, your electron density expression should be slightly, only slightly modified. So my suggestion is, please come back to your dormitory room or library, then please rework your previous derivation about MOS capacitor. Just to assume that in this case, please assume that you have 0 vanishing hole quasi-Fermi potential, but your electron quasi-Fermi potential can be regarded as just V. Then please rework your derivation. Then you will find that the modification is quite much limited and concentrated. Only one term, one single term is modified by this new expression for your electron density. I think that will be quite much helpful for your understanding on this problem. Okay, although I have spent the entire lecture material for this gradual channel approximation and Pausa integral, but since this part is at the center of our second part, I cannot speed up. So I'm willing to spend more lecture slots to explain this model development. So please expect one or two more sessions on this stuff.